In this video, we're going to introduce the concept of a precise definition of a limit. So far in this class, we've talked about arbitrarily close to as a limit. And for example, like if we consider the function y equals 2 of x minus 1. Well, we know what the graph of that is. That's a linear function with a y-intercept at -1 and a slope of +2. It looks roughly like this. And we know there's a point on this graph that we could say is 4, 7. Okay, so if I said to you, what is the limit as x approaches 4 of 2x minus 1, you would say 7. Because as we come to x equals 4 from either side, as we travel along that graph in either direction, my y value tends towards my limit, 7. And in this case, the function is defined at that point, so it's very easy for us to see. But what we're going to talk about in this precise definition of a limit video is how we can replace that phrase arbitrarily close to. We want to know, as we are within a specific space, a specific quantity of closeness, not an arbitrary closeness, right? Because 3 feet is arbitrarily close. 2 inches is arbitrarily close, right? And those are very different distances. So if we specify, we say, okay, well, I'm going to give you this value, and that's how close you need to be. We will be able to define how close we need to become or come to that x value on our x-axis. So here, I've brought in a picture of exactly what this line looks like to kind of help us explain what we're going to be doing better. Essentially, I'm saying, all right, well, maybe I can't get to that point. Maybe there's an open circle there and I can't get exactly to this point. Okay, so how close do I need to be that I can show that I'm within an acceptable range of this limit? So what we're going to talk about is we'll be given a distance off of the limit, which we'll call epsilon, and we'll say, well, we want this satisfied. I want to prove that I'm within exactly 2 units of the limit 7. And in order for me to prove that, I will determine and specify, well, that means I would have to be within 1 unit of x equals 4. Okay? And so we're going to talk about having these epsilon and delta values. So as long as I choose my x between 3 and 5, 1 unit off of 4, I know that my limit will be within 2 units of 7. And you're saying, well, Ms. Stein, 2 units, 1 unit, that's not very small. We can get much, much closer to something, right? Clearly, 1 over a million is much, much smaller than this space 1 or 2. But for the sake of realizing and visualizing this situation, we use a reasonably small value, say 1 or 2. And we understand that if we want to prove it to be much closer, we can use a much, much, much smaller value, and that would also provide the same type of calculation. So let's consider this precise definition. All right, we've already talked about the idea of a limit. And we've said, if we have a function f, which is on some horizontal open interval approaching that c value, okay? And it's defined everywhere on that interval except possibly at c. Then we can say the limit would approach some number L. Okay, and we write it using this format. So what our precise definition says is that I can choose some positive epsilon value. And if I'm given a positive epsilon value, think about it as like my vertical error off the limit, right? The limit is always going to be on the y-axis. It's a y value. And so if I'm prescribed and said I'm allowed to be within epsilon units off that limit, and then we can call this a precise definition. So if I'm given a positive epsilon, epsilon being, a small distance above and below that limit, then there must exist a corresponding delta on the x-axis that is positive, such that I'm only delta units away. Okay, so the main things we want to remember when we start talking about this precise definition of a limit is basically given an epsilon, given a margin of error off my limit, epsilon, I can determine a delta, which is a prescribed distance or a margin of error off of my x or c value that I'm looking to approach. And so visualizing this just a little bit more, we may know that as x approaches c, which may or may not be defined, that there exists a limit. Okay, so we know as x approaches c, there's a limit. We are approaching some specific y value. And so if I say, well, you have to be within epsilon units above or epsilon units below. We've got plus epsilon and minus epsilon there. So as long as you are within epsilon units off, then I know, as long as I choose my horizontal interval, my closeness to C, to be within this delta off, I will always be in that allowable epsilon window. Okay, so delta and epsilon, they represent small changes in the function. They describe arbitrarily small or a specifically chosen small, say 1 unit or 1/10 of a unit or 1/100th of a unit. They describe arbitrarily small prescribed errors. So let's look at an example. So here we are going to show that the limit as x approaches the value 1 of this function 5x minus 3 equals 2. I mean, obviously we know I can plug 1 into the function. 5 times 1 is 5 minus 3 gives me 2. We know that's true, but we want to prove that because in some situations we may be dealing with a function where we can't plug that in, all right? But for the sake of keeping this example easy, we use something that's very easy for us to see visually. So in this case, my C value is equal to 1. My function is the 5x minus 3. And my limit value is 2. So these are the things we know. And what our precise definition says is that for any given positive epsilon, we must also find a suitable positive delta. And we need to do this so that if x cannot equal 1 or x is not equal to 1, and that x is within a suitable distance of c equals 1, so that suitable horizontal distance is my delta, then we would know it is true that the function is within epsilon, my small vertical prescribed error, epsilon, distance of that limit, L equals 2. Or rather, we can say when 0 less than x minus c, and my c value is 1. So as long as that is less than delta, then my function minus the limit, and the limit is 2, would be less than epsilon. So we almost always start with epsilon and we work backwards to find delta. So I'm going to start with this piece, f of x minus 2, absolute value of that less than epsilon, which I've written right here. Okay, so f of x was given. F of x is 5x minus 3. So I have 5x minus 3 minus that 2 value from my limit needs to be less than epsilon. So we're going to try and manipulate this to create this same prescribed error for delta. So in this situation, I can simplify that. That is 5x minus 3 minus 2 is minus 5, less than epsilon. In this situation, I can factor out a 5. So that is 5x minus 1, less than epsilon. The absolute value of 5 is just 5, so I can pull that out. And I can say, well, x minus 1 is less than epsilon divided by 5. And so if you look at this, x minus 1 needs to be less than epsilon over 5, and you relate that up here, all right, this allows us to take delta to be epsilon over 5, because you see that similarity. So we'll write, thus, delta equals epsilon over 5. And so now I'm going to double back down and go in the reverse direction, go forwards, go from delta, and show you that if I do allow this, I will get that same epsilon. So we're going to say if 0 is less than x minus 1 is less than delta. So since I have allowed delta to be epsilon over 5, I can rewrite this. I left an absolute value bar off. Which means then that my function value, and again, when I do that double barred arrow, I mean the word then, the absolute value of my function value minus 2 equals epsilon. So that's the same as 5x minus 3 minus 2 equals epsilon, or 5x minus 5 equals epsilon. We can factor that 5 out. So 5 times x minus 1 equals epsilon. So I want to turn this epsilon into a delta. So on the right here, I can multiply by 5 over 5, which is the same as multiplying by 1. And, I can rearrange the way that looks. I could say, well, we're multiplying times 5 and divide by 5. And so what we said, epsilon over 5 is equal to delta. So I'm going to take this here and throw my delta in. And you can see then I have a 5 on either side of the equation. So if I divide by 5 on both sides of the equation, those would cancel. And 5 divided by 5 cancels on either side, and I have x minus 1 equals delta. So I've proven this full circle. When I'm done, I like to put 3 dots in a triangle. That means therefore. And so keep in mind, we only need a positive delta that will work. We do not need the best delta. We just need any positive delta value that functions in this situation. And if we have a small delta, then we know any other smaller delta will do. So I hope that helps. I encourage you to work through the video, take your notes, try to make sense of this epsilon and delta definition, the precise definition of a limit, because it's generally a hard concept in my experience for students to wrap their brains around. But once you get it, it makes a lot of sense. So I've done my best to explain it using as many words as I can. So I hope it wasn't too wordy.